So in this part of the presentation we're going to look at disk encryption and try and understand the different methods and techniques that are used in forms of keeping our disks secure. Okay, so just to recap, so we'll be coming back on to this in a little to see how this applies to disk encryption. But really the workhorse of what we have in terms of cryptography is good old symmetric key encryption, and typically focused on this one here, AES. So with symmetric key encryption we use one key to encrypt and another key to be able to decrypt. The other method that we've came across is public key. With public key we have two keys. One key is used to encrypt and the other is used to decrypt. We'll actually find that these two methods work together very well. This one used for the encryption, this one used to protect the key that we use to be able to encrypt our disks. And the last method is the one-way hash, where we want to be able to create a fingerprint to be able to make sure that what we've stored is actually still what we think it is. Okay, so we'll come on to this in more detail, but basically what happens, and we'll see this also in the next unit, is that we have a key pair and we create an encryption key that we're going to use to encrypt the disk. And what we do is we protect the encryption key by encrypting it with our public key, and then obviously our private key is then used to be able to decrypt that and pull off the key that's used to decrypt. So this is a fairly standard method that's actually used, and we can see here that public key and private key or symmetric encryption are being used together quite happily. Okay, so we can either encrypt our full disk, so this involves encrypting the boot partition and so on to make sure that we can have a secure boot up. So we might have a laptop where the whole of the disk is encrypted, even the operating system components and so on are encrypted. So with this, obviously, if we lose the encryption keys or the methods which are used to boot the system up, then we will lose the whole disk. The other type that we have is to be able to encrypt just a file, a single file, or a folder, and that's file and encryption folder. By far the market leader in terms of disk encryption is Microsoft Bitlocker. It's a proprietary method and it's integrated into Windows 7, 8 and so on. An advantage with it, it will link to an Active Directory infrastructure where the keys can actually be stored inside the Active Directory domain controller. The other one that is popular in the market is TrueCrypt, and TrueCrypt is an open source package that will run quite happily on Windows, Mac OS, or even on Linux. And the other ones that we have Checkpoint, Disk Encryption, Sophos also have a product alongside Symantec and so on. Bitdefender is a fairly popular one along with Kaspersky Labs products. But the main market leader is this Microsoft Bitlocker, and TrueCrypt is used fairly often too. In terms of the robustness of the security, we have 4 different levels as defined by FIPS, the FIPS standard, Federal Information Processing Standards, which is led by NIST. So the most important standard is FIPS 142, which was released in May 2001. But there's also a new standard, FIPS 143. And with this software is limited to level 1 and level 2. So with FIPS we have the certification process where the security product fits into one of these levels. Obviously the higher that we go up, the more secure the infrastructure actually is. FIPS level 1 is the lowest level security, very little security really applied onto it. As we go up to and above, then the operating system itself must be compliant with the with level 2 and so on. So at this level, level 2, we have some sort of physical tamper evidence on it, and we have role-based authentication. So role is typically that you have a certain role, such as administrator or staff or students, and that allows you access to your security product. At level 3, we now get the concept of an identity access, and also that there is some isolation between the user and the back-end security infrastructure. This can either be a physical separation or a logical one, such as through a firewall and so on. And there is some barrier between the place that the parameters are entered and the place that they're actually passed into the security infrastructure. At level 4, we have the highest level, and this is where we have much more physical security requirements, such as inside a guarded building and so on, and also robustness against environmental attacks, such as through power supply power failures and so on. Okay, so the ways that we can actually authenticate the user and get rights onto the encrypted system is obviously a username and a passphrase. USB stick, so we can store the encryption keys on a USB stick, and the machine won't boot up unless we put the USB device into the machine. We can have a one-time password device, such as an RSA token, that would allow the user to read off the value and then enter that as a PIN number onto the system. And then in the ultimate case, we can have a biometric device, such as a fingerprint reader, that will actually link to a TPM chip on the device. So increasingly mobile devices are using this method. The latest Apple iOS has a TPM chip that will link to the fingerprint reader, and it is there that the encryption keys are burnt into the system. Google too is looking at this, where we have an encryption by default and where the encryption keys are stored inside the TPM module on the device. With laptops too, we can have a TPM chip, and this is where the encryption keys are actually held. Along with each of the individual ones, we can actually have two or more of these methods that come together to make the system even more secure. So we could have a passphrase and also a USB drive with encryption keys. Okay, so what we normally have is that the secure documents themselves isn't actually that popular, and we're often running standard packages. So as far as Excel and Word actually knows, that they're still dealing with the same old disk system and the same old directory structure. So all the partitions and so on still appear the same, but underneath, the data that's actually stored on the disk is actually encrypted data. So there's normally an encryption layer that sits in between this document access layer, or the API, and the storage layer. Increasingly also, we will have a cloud storage, so that the data is stored, mounted as a drive, and then stored onto the cloud in an encrypted format. So this can be in the form of a whole disk image that's encrypted, or even as a single file. We can actually mount that as a drive. A key important thing is that once the data is unencrypted, in memory it's non-encrypted. Also, if we put it onto other storage, it will be non-encrypted, and the same goes if we email any of the documents. They will be non-encrypted in transit, and we need to use secure email if we want to keep it secure. Okay, so now let's look at the two main methods that we might use in terms of our disk encryption. First, we'll look at Bitlocker and the encrypted file system, and then we'll look at TrueCrypt. Both have different ways of operating. Okay, so with Bitlocker, what we have is two drives, and they're NTFS because FAT isn't really a secure file system. So we use NTFS. One is the boot drive, and that's unencrypted, and the other one is a completely encrypted drive. So this is the one that boots up, and then it will actually get the keys to be able to open this one up. So there's three main methods that we can use in Bitlocker. We can use the TPM chip, or we can use user authentication, or a USB key mode. So with the TPM, what we have is that the encryption keys are stored, sealed in this chip on the device, and then the operating system opens up the keys on the chip and allows the machine to be able to boot up. The user authentication mode has a pre-boot PIN integrated into it. And then the last one is our USB key, where the user has to insert a USB key as a startup key so that the operating system can actually boot into the encrypted drive. So it's important that we have a machine that the BIOS supports the reading of the USB devices before it's actually into the operating system. The other method that we have is the electronic file system that will perform drive or folder encryption. We'll have a look at that in a little minute. With the electronic file system, what we have is that we have a key pair, a public and a private key, and that's stored in your certificate store on the machine. So here that we are here, and what I'll do is I'll just show you the key store. Okay, so on our machine, Internet Options, and here we are. Okay, so what I'll do is I'll just actually delete this certificate, which is in there, so that we can actually start again. So this is your personal certificates, and those are stored and loaded up whenever we do anything on the system related to digital certificates. Okay, so just let's close that. Okay, so when we encrypt with our file system, we end up with a key pair, and we should get a certificate that has both the public and the private key in it. So these are normally stored in a PFX file with a password. And we can also have a cert file which contains the certificate or the public key. So the cert file can be used to be able to read the data, but if we want to actually modify it at all, then we would need the PFX file imported. Okay, so as we've previously seen, we create typically with AES. We have our encryption key. The public key is used to encrypt the key and then put in as a header. The disk itself is then encrypted with the encryption key here, so that the system itself reads the certificate, reads the private key of there. The private key opens up the encryption key that's used, has been used to encrypt the disk. Take that off, and then that is used to decrypt the files. If we don't have that certificate on our machine, we can't read the files. So let's take an example here. So what I'm going to do is I'm going to create an encrypted drive. Here. Okay, so let's take this one here. So let's just we'll just create a new drive. And we'll create it here. So we'll just call it encryption new 123. Okay, so we can encrypt that. So the encryption only works with NTFS, so it needs to be done there. Okay, so that's, we go to advanced and then encrypt the contents. And then what you should find, it turns green here, and then anything that we create in here is actually encrypted. So what we'll do is we'll create a new Word document, and we see that goes green too. Okay, so all our folders and things like that are encrypted. So what we obviously need to see is where the actual keys are, and as I said, you should find them in your certificate store, and those will be the keys that we will use to be able to encrypt and decrypt the files. Okay, so once you've encrypted it, a message may appear for you to be able to store your keys on a USB stick. But what we'll do is we'll have a little look to see if we can determine the keys. So I think it was new encryption. Let's check what the file was called. New underscore. Okay, so let's go into that folder. Let's just check what the folder's called. It's called Encrypted New. Okay, so we can see that there's thumbprint, there's AES 256-bit keys. Okay, so the next thing we want to do is we want to be able to export our keys from there, and so we do that with our -r option, so you can actually have a look to see the various options that we have, but we use cipher/r, and then so it's encrypt. So let's go into that one. So cipher/r. Okay, so we give it a password there, and there we go. So those are the two files that we really need in terms of to be able to read the file. So there's one. So you can see that one doesn't have a public key on. That doesn't have a private key. So you can see from here, no private key. We can install the certificate if we want. And the other one is our PFX file, and then we can import that in there. Okay, and then we would put our password in there, and with that we can just enter our password. There we go, so that's imported. So we'll just have a quick look back just to see that it's imported okay. There we go. Okay, so you can see there I've got the private key for that certificate. Looks a bit strange here because it's 2014. You go, well, that's not got very long to actually be valid, but actually the end date is 2114, which is 100 years into the future, so it should still be valid for that one. Okay, so this one you can see is a self-signed certificate, and it's for our encryption. Signed for that, EFS file encryption, and that's it. Okay, so we should be able to then access our files, and if we lose our certificates, we can import them back in again. So in the tutorial, what you'll find is that if you delete your certificate and then reboot the machine, you won't be able to access the files anymore. Okay, so if you lose these, or if you lose the digital certificate, you won't be able to decrypt the contents of the encrypted folders. The certificates themselves can, obviously, they are protected under password. What we can actually do is that, or an intruder can actually perform a dictionary attack against a PFX file by continually trying lots of usernames and lots of passwords, and eventually getting one that matches. You can see here the password is above. So an intruder can actually find out what the password is. So you need to make sure that the passwords on them aren't in standard dictionaries, or they can be open to being cracked. Okay, so I'll just illustrate this. Right, so this gives us our first chance to go onto the virtual machine. So here we go. So on the virtual machine, we've created two virtual machines for you. One is a Windows one, and the other one is a Kali Linux one. And we'll be transferring between the two for the tutorial, just to show that we can actually take our TrueCrypt from one machine and then import it on another machine. Right, so this is our Linux Kali one. So what we'll do is we'll just go to our Windows one, and that one's already powered up, so we'll just go with that one. And if you want, you can power up your Linux Kali one and then open up the console. What we've also done is we've enabled you to be able to mount a USB stick onto your drive. Okay, so this is the option that you use here. Put in your USB stick onto your machine, and then it should be able to put onto your, you should be able to mount it onto your vCenter instance. Okay, so here we are. That's our Windows machine, and we've created a little program that you can use called Network Sims. Just takes a minute to start up. And then what you should find in Network Sims is a little toolkit program. And this little toolkit program will allow you to crack the digital certificate. Okay, that's starting up. Okay, so if you go to toolkit, run the toolkit. It's got various bits and pieces in here, but we'll go to encryption and then digital certificate. And if you then open up your certificate, just download one, there's one there. Okay, then goes through, and whenever you see something appear here, it means that it's actually cracked it. It's taken a while, there you go, it's found it. Okay, so we'll update this so that it actually shows you, it will stop when it actually finds the key. But if you go through the there we go, that's it there. If you go through all the ones it's tried, you can see it's been successful there. So apples is the password. What happens is that it gets an exception each time it tries these ones until it finds one that works. So what we'll do is we'll open up the file, and you can see it's been successful with that one there. Okay, so that's the way our PFX files can be under attack. Even though we use fantastic encryption, it's actually still protected by a password. So the other popular method that we have in terms of our file and disk encryption is TrueCrypt. So TrueCrypt has advantages of being open source. It also supports a wide range of operating systems, and it's basically free. Unfortunately, its main disadvantage is that if you lose the passphrase, then it's almost impossible to recover the disk. Also, the current support for it is a little bit patchy, as we'll actually see. So it uses this method here, this PBKDFS2 method, to take a password and some salt to create a key, which is then used to encrypt the header. The header is then, once we've opened that, we can find out the key that's been used to encrypt the disk. The three main methods of encryption used are AES, that's Raindal, and two of the other finalists from the AES competition, which is Serpent, produced by Ross Anderson, and Two Fish, produced by Bruce Nair. They're 256-bit keys with 128-bit blocks. So we can also take different methods for authentication, such as RIP EMD 160 or SHA 512 and Whirlpool. We can also put multiple methods together, such as Serpent and AES. AES Serpent means that Serpent first for every 128-bit block, and AES second. It gives us more security, but obviously it has an overhead in creating them. Okay, so we typically create our volume. We then define the encryption and the hashing method, create the volume itself, and then what we would do is to take that and then mount it as a drive onto our disk. Okay, just like we have here. Okay, so what I'm going to do is I'm going to set up TrueCrypt here. So just let me unmount a drive. Okay, so I'm going to create a volume as an encrypted file container. So that's a single file, not a partition, and we have a standard volume. It's also possible to put a hidden partition inside our file, but we'll just create a standard one, and then I'm just going to call it build test 10. Okay, so we can take each of the different methods, we can benchmark them if we want, and then we can use different hashing method. So just let's benchmark just to see what the different speeds are, but AES wins by a long way normally, and so it's just trying on my machine. It's got 2 threads, so you can see there that AES is beating Two Fish by about a factor of 3 or 4, and then all the other ones are much slower. This one is 10 times slower than the AES, so we'll take that one and we'll just go for SHA 512. For NTFS we need about 4 meg, so we'll go for that. We'll go for 5 and then put our password in. Now we'll select the bar format, so we'll just go for FAT, and then we'll do some random stuff and format it, and that's it. So let's select our file, and let's just mount it. There we go. Okay, so we're all mounted now there, and we'll just have a look. We can see there's an AES 256, there's the SHA 512, and so on. So we should find that when we go to our W drive in this case, that's been mounted, so we can actually start to create some files in there. Then everything that's stored on there will actually be encrypted. Then what we typically do is that we will then, so we can actually have a look on the command line. There's the W drive, there's our file. So when we're happy with that, we can then dismount it, and then that becomes our file that we can actually use. Okay, we can send that away as an email, and then through an out-of-band method we can actually send the password to the other side, and then they can then decrypt it. Okay, so it was created about 2004 as open source by these Czech developers, and everything is fine up to version 7.1. That 7.1 is what we've been using, but there was an audit of the code, and then there was an announcement on the 28th of May that they were going to discontinue TrueCrypt, and the 7.2 was released, but it was intentionally crippled. So if you make sure that you get this version, then everything should be fine. So this was the message that actually appeared on their website, and they were advising people to move to Bitlocker instead for that one, this Bitlocker here. Which sounds a bit strange for open source developers to actually say that users should go towards a closed source proprietary operating system. Luckily, sites have appeared which are forking the code, such as TrueCrypt.ch in Switzerland, that's actually now continuing to develop TrueCrypt. As a last little thing, let's look at if we can detect encryption or at least compression on our files. So what you find is that there's very little way of determining that something's encrypted, because if you looked at the byte formats, there is no magic number there at all, and if you actually printed each of these as a dot, as a grayscale, you end up with complete noise in it. So it's certainly one way that you can actually detect. If you detect that a file is completely noisy, then it looks like it's an encrypted file format. So this is from TrueCrypt, and it's very difficult to know that it's actually TrueCrypt or any type of cryptography. With compression though, there is what's called a magic number at the start of the file. So if you detect this sequence, 54B0304, then it's a PKZip file. 1F8B08 is a gzip file, and so on. So with a hex viewer, you can actually view the file. What we'll do is we'll use a security site to be able to have a little look at this. So you should find this on Digital Forensics, and here is our magic numbers. So these are all the magic numbers that we get. So there's our PKZip. If we actually load up our PKZip, you can see at the very start of the file we see that sequence. Let's try another one. Same sequence, and another one. Same sequence. Okay, so in that case you can actually see that it's possible to be able to determine compressed file formats, but unfortunately we can't find out encrypted file formats or the method that was used. Okay, so that's been an introduction to disk encryption, typically focusing on how we store keys in a certificate, and also how we can access our encrypted content through a passphrase.